Hello. So we come to the last and concluding lecture in this series on differential equations. So today's lecture will be looking at some odds and ends, or maybe is ahead if you like. So the issues that we discuss today will be as follows: some uses of differential inequalities, but this will be very similar to the way we worked with linear differential equations, and then we'll converge towards a uniqueness theorem, but we shall not exactly reach there. We shall not state the uniqueness theorem. The pendulum equation again. We started this lecture series by deriving the pendulum equation. That was the first differential equation that we derived, and we shall also end by looking at the pendulum equation a little more closely, and then a few concluding remarks. And so let's begin. How to use differential inequalities. Now let us look at this differential equation 4.1. dy by dx equals y into x plus y, with the initial conditions y of 0 equal to 0. You see, this differential equation 4.1 is a Bernoulli equation. It's a Bernoulli equation, and so you want to divide by y squared, but unfortunately you cannot. Why? Because y of 0 is 0 and division by 0 is not allowed. So how would you solve 4.1? Well, you see that the 0 solution is already a solution. Take the constant solution 0, it satisfies the differential equation. The derivative of 0 is 0, and the right hand side is also 0. So plug in the constant solution y equal to 0 in 4.1, and you see at once that it's a solution of the differential equation. It also satisfies the initial condition y of 0 equal to 0. But have we completely solved 4.1? How do we know that there are no other solutions of 4.1 satisfying y of 0 equal to 0? Maybe there are others besides the 0 solution which will satisfy 4.1. How do we rule out that possibility? We need a general theorem, a general uniqueness theorem that guarantees that the 0 solution is the only solution of 4.1 and that there are no other solutions. So you see the need for a general uniqueness theorem already in this very simple situation. So let us go back to the very first lecture where we discussed differential inequalities, where we knocked off some terms in the differential equation and got a differential inequality when we were discussing escape to infinity in finite time. Well, so let's look at the differential equation 4.1. dy by dx equal to xy plus y squared. The y squared term is always positive. So let us look at the differential equation dy by dx equal to xy plus y squared. The y squared term is always positive. So let's see. So we can write dy by dx minus xy greater than or equal to 0. I had knocked off the y squared term from the differential equation 4.1. From the 4.1, I have knocked off the y squared term. So from the differential equation, I got the differential inequality 4.2 dy by dx minus xy greater than or equal to 0. Now, how do we proceed? Now, suppose if in 4.2 you had an equality instead of an inequality, then 4.2 would be a linear differential equation, right? So how would you proceed in that case? You would multiply the 4.2 by e to the power minus x squared by 2, right? But do the same thing here. Never mind, it's an inequality, but e to the power minus x squared by 2 is always positive. So I can jolly well multiply 4.2 by e to the power minus x squared by 2, and the left hand side of 4.2 becomes an exact derivative, namely ddx of y of x into e to the power minus x squared by 2 greater than or equal to 0, which is 4.3 in the displayed slide. Well, what do we do now? We have to integrate 4.3. We have to integrate 4.3. So let's proceed. You got the following situation. Let's see. You got a function phi of x which is always non-negative. on an interval AB. Then we can say integral phi of x dx from a to b is surely non-negative. You will agree with me on that. Why? Because what is the integral? The integral is the area under the graph, the area under the graph y equal to phi of x between x equal to a, x equal to b and y equal to 0. But what does this inequality tell you? The inequality tells you that the phi of x, the graph of phi of x lies above the x-axis. If the graph lies above the x-axis, then the area under the graph is going to be always positive. And that's all that you need to say to prove this. So in particular, if you have two functions fx and gx, and if fx is greater than or equal to gx on the interval ab, then integral a to b fx dx will be greater than or equal to integral a to b gx dx. How do you get this? You get this from the previous one. Simply take phi equal to f minus g. Simply take phi equal to f minus g in the previous one and you get this one. Okay, so let's apply this. So let's go back to the slides. You see, you got 4.3. So I say that integral on the left hand side will be greater than or equal to integral on the right hand side. In other words, the integral of the derivative from 0 to x. I am going to integrate both sides of 4.3 from 0 to x. Okay. So I am going to integrate both sides from 0 to x. When you integrate a derivative, you use the fundamental theorem of calculus. So you got d dx of y of x e to the power minus x squared by 2 greater than or equal to 0. So integral 0 to x d dt of y of t e to the power minus t squared by 2 dt greater than or equal to 0. Of course, in the definite integral, the variable is a dummy variable. So let's use the fundamental theorem of calculus. Y of x e to the power minus x squared by 2 minus y of 0 e to the power minus 0 squared by 2 greater than or equal to 0. This is 1 and y of 0, remember, was 0. Therefore, we get y of x is greater than or equal to e to the power x squared by 2 into 0, which is 0. So we have concluded that the solution is non-negative. We have concluded that y of x is non-negative if x is greater than or equal to 0. Now we shall show that y of x is actually equal to 0. Let's proceed. Now we know that y of 0 is 0 and y is continuous, and therefore if the value of the function at the origin is 0, then the value of the function must be less than 1 in a certain piece around 0, namely 0 to c. So on the interval 0 to c, we know that y of x must be less than 1. If y of x is less than 1 and y of x is already non-negative, y of x squared must be less than or equal to y of x. So let us go back to the differential equation. What does the differential equation say? It says dy by dx equals xy plus y squared, but now we have seen that y squared is going to be less than y. So let's use this inequality now. So since y squared is less than y, from 4.1 we get the differential inequality dy by dx is less than or equal to x plus 1y on the piece 0 to c. So again do the same thing, again imitate as if you are solving a differential equation. Proceed as though you are going to solve a linear differential equation, namely you multiply the differential equation by e to the power integral px dx. What is px in this case? Minus x plus 1. And then you will conclude exactly as we proceeded just now, y of x is less than or equal to 0. And so combining the two, we see that y of x must be identically 0 on this piece 0 to c. But now we want to show that not only is y of x identically 0 on the piece 0 to c, it must be 0 everywhere. You can actually show that it is going to be 0 everywhere. Proceed by contradiction. Suppose it is 0 up to a certain interval, after which it becomes positive, then try to arrive at a contradiction. Be slightly careful if you are working this proof out. Okay. So now let me give you a couple of exercises. Try the same idea on these two differential equations that you see in the slide. The same idea of knocking off some terms, getting an inequality and proceeding. So I worked out one example in detail and I'm asking you to try out two others. So the two differential equations are dy by dx equal to y into y plus square root of 1 plus x cube. The other one is dy by dx equals y into y to the power 3 plus sine squared x. For both these differential equations, y of 0 is 0. And so by inspection, you see that 0 is a solution. What you need to establish is that it is the only solution. So proceed as I have indicated in the last exercise. So what's the point of this exercise? Isn't there a simpler and more direct approach to arrive at this conclusion? Each time you encounter a situation where you have to divide by y or y squared, as it happened in the Bernoulli equation, and the initial condition says y of 0 equal to 0, are we going through this rigmarole each and every time? What you need really is a general uniqueness theorem. General uniqueness theorem that can be directly employed off the shelf. You pick up a uniqueness theorem. Importance of proving such uniqueness theorem is now slowly dawning upon us. And how do we prove such uniqueness theorems? The point that I want to make is that these examples that we have just worked out are rather typical models of reasoning which will give you a proof of the uniqueness theorem. Idea is to obtain a differential inequality and then proceed exactly as we solve a linear differential equation. And we shall not prove the general existence theorem, but the key ingredient is the idea in the following slide. So suppose f of t is a non-negative function on an interval ab such that f of t is less than or equal to a plus b integral a to t fs ds. Inequality 4.4. That's a hypothesis. A and b are constants and f is non-negative. Then the conclusion is inequality 4.5, namely f of t less than or equal to a exponential of b times t minus a. Idea of this proof is exactly similar. Call the right hand side of 4.4 as capital F of t. Capital F of t is a plus b integral a to t fs ds. Then notice that little f is less than or equal to capital F. Little f is less than or equal to capital F, and capital F evaluated at little a is capital A. 4.7. What do you do next? Differentiate 4.6. Differentiate 4.6, what do you get? df by dt equal to bf, right? You use a fundamental theorem of calculus to differentiate 4.6. df by dt equal to b times little f. But b times little f is less than or equal to b times capital F. You got a differential inequality. You will proceed exactly as you do with a linear equation. Multiply the differential equation by e to the power minus b into t.